Is let's take a look at a couple problems that came up, and so let's get those Chromebooks. I really want everybody to follow this stuff. You'll get time, and I mean, what I'm doing today is gonna, if anything, will push back you. It's not gonna, I don't want to encroach on work time, I just want to build in some time. This gives you extra days to get caught up when I'm going through these things. There are a couple topics that, you might remember me saying this, but earlier in the year when we were thinking we were gonna be gung-ho AP bound, there were a few things that I said that I really like to cover that I didn't cover. And one of them was called the squeeze theorem. It's really an important theorem in calculus. It's a picture theorem. It's one that I really want you to be familiar with. I'd always intended to come back like after the AP test and do it, but it would help to talk about it now. So I'm going to go back and backfill a couple things that I sort of glossed over that normally I would have taught by now. But I don't want to push these things out just to prepare for a test, because I think they really are important topics. So let's look at a couple things here. There's some questions on the test that get at an important concept, and that is discontinuities, types of discontinuities. Real quick, what are the different, essentially, what are the two categories of discontinuities? Tyler, what's one of them? Removable. Removable. What's the other one? Non-removable. What's the difference?
One point versus infinite points.
1 point versus infinite points. Removable, we can either define a point to fill in a hole, or we can move a point to fill in a hole, right? But we're only having to redefine a single point, that's doable. Non-removable means we have to move an infinite number of points, whether it's an asymptote or even just a break in the function. That's a much larger scale project. So we want to be able to talk about the types of discontinuities that we see here. But what about this function, f of x equals sine of 1 over x? Talk to me about that. Where does it have a discontinuity? Zero. How come? You're right. Why is that? What's going on there, Maisie? Why would this have a discontinuity at 0? What's bad about the number 0 for this function? It's in the denominator. You can't divide by 0, right? Even if it's inside of a trig function, dividing by 0 is forbidden. You can't do that. So we have to omit, we've got this. So we have to omit 0 from the domain, right? What's going on there? Is that a removable or a non-removable discontinuity? Now, we talked about this one specifically in Unit 1, but it's been a while. What's the behavior of that sine of 1 over x going to be as x approaches 0? Because that's the point, that's the discontinuity, right? It's oscillating, isn't it, right? And if we look at it, let's look at a graph, because this is really interesting, and this is really cool stuff. Hopefully you'll like this, because I like this. So it's doing this kind of thing. That's the wrong one. I gotta save this real quick. Hang on. This is let's go back to this guy. So if I zoom in, remember that one? That's it, right? And do we understand that behavior? As x approaches 0, 1 over x is going to approach infinity, right? So the angles we go through just get huge. Between this point right here, let's say at x equals 1, and here at x equals 0, we would have to use an infinite amount of ink, right? Because the curve is going to have to go, we're going to have to put in angles that go all the way from 1 to infinity, which you can't do, right? So this thing just oscillates madly and it never settles on anything. And so would that be removable or non-removable? Non-removable, right? We'd have to move an infinite number of points to make this thing whole, right? To remove that discontinuity, okay? What about, though, this changes things. If we multiply by x, it doesn't seem like much, but that changes everything, right? Now, what is that doing? If we multiply by x, the problem is still going to be at 0, right? So I guess this one right here is non-removable. about this one? Well, x still cannot equal 0 because we're dividing by 0, right? But can anybody discuss that one? What's going on with that one? There's a couple ways we can get at an answer here, but there's a way I'm going to show you in a little bit that's the best. As x approaches 0, we get a product of two factors. Kirk, what's going on with that factor? Going to 0. And it's going all the way, right? I mean, it's approaching, it's getting arbitrarily small. What's happening to the outputs of this one? They're oscillating, but what can you tell me about the values? The output of a sine function? It's going to be trapped, right? It's going to be trapped between -1 and +1. And what's going to happen if I'm taking the limit of two factors, and this is a little strange, right? If we're taking the limit of g of x as x approaches 0, we're going to get 0 times, well, how do we represent that? It's just going to be some trapped number. It's going to be trapped on the interval from -1 to 1, right? Those are finite numbers, though. 0 times a finite number is what? 0, right? So the limit here is 0, right? And so you see that, what do you think is going to happen then? Is that one going to be removable or non-removable? It's going to be removable, right? Because it's going to pinch down to a point. So here's one way to, we can visualize it. So if we multiply by x, look what it does. Right? It takes that same function and it just pinches it down to 0 in the middle, right? So you can see there that, you know, that this thing is going to have just a single pole at 0, 0, right? So we can see it. We can kind of talk our way into it by just looking at the fact that we've got 0 times a trapped number. That's just, I mean, it's a good argument, but it's a little bit hokey. It's not like it's an ironclad proof. So here's really the mechanism we need in calculus to make that a little better proof. We need the squeeze theorem. Okay, what's the squeeze theorem say? It's nothing so profound. It's all, this picture tells the whole story. Squeeze theorem, this is just in section 1.8 in your textbook. It's in the PDF for section, you know, back when we talked about limits, it's in that section. Oh, it's not in section 1.8. It's theorem 1.8. It's in section 1.2. It's in section 1.2. It's in the PDF at the start of section 1.2. It's in the textbook. Here's what it says. If some function h of x is less than or equal to f of x, and f of x is less than or equal to g of x, so a better way of saying that would be f of x is greater than or equal to h of x and less than or equal to g of x. For all x in some open interval containing c. So if we go way out yonder to the left or right, that might get flipped around, but we don't care. As long as we're in the neighborhood of values surrounding c, which is the point of interest, if we maintain that relationship, that's all we care about. That g of x is the ceiling function, h of x is the floor function, and f of x is pinched in between, right? And they could graze each other as long as f of x is less than or equal to g of x and greater than or equal to h of x. I mean, they could actually, like, it could come up here and graze that thing, but as long as it doesn't ever get greater than g of x or less than h of x, it's contained inside that sandwich. Sometimes this is called the sandwich theorem, squeeze theorem or sandwich theorem. So if that's true, then if the limit of h of x as x approaches c is L, and the limit of g of x as x approaches c is L, what does that say about the limit of f of x? It's got to be L, right? If the ceiling function and the floor function both converge to L, and f of x is guaranteed to be pinched in between those two, it's going to get squeezed to L also, right? And so it's really not that big a deal. It's all just, that picture says everything about the theorem, right? But it's very useful here. So if we go back to this example right here, could we invoke that theorem? if g of x is, in this case, let's make it f of x. Let's go to the next page and we'll make it f of x. So if the in-between one is the sandwiched function is f of x equals x times sine x, and, sine of 1 over x. And 0 is the point of interest, right? That we want to take limits as we approach 0. Can you guys come up with a ceiling function and a floor function that would always encapsulate that on some interval containing 0? You already told me that the maximum value that a sine function could have is positive 1, right? And the minimum value it could have is negative 1. So what do you think? So how about that? Absolute value of x. That would be that could be the function that is the ceiling function. What would be the floor function then? Negative absolute value of x. Yeah, let's look at this. So there's f of x, right? We'll even get the colors right. This one was supposed to be black, right? To match that one's black. And then the ceiling function is absolute value of x. That one should be, wasn't that red? I think it was. Yeah, it was red. So let's make that guy red. Everybody agree that's a ceiling function, right? It's never the weird oscillating sine function is always going to, it's never going to exceed that on the top. And then on the bottom, I think it was blue. Purple's close enough. Look what we get, right? You can visually see that then. Because the limits of g of x and h of x as x approaches 0 both go to 0, this thing has to converge at 0, right? Anybody see that? And if that's true, if the limit of f of x which x times sine of 1 over x as x approaches 0 equals 0, it has to be removable discontinuity. Right? In other words, we can't draw it on here, but there is a hole right in the center of that thing, right, that we could fill in by just with a single point. That's pretty cool. What do you think? That's kind of aesthetically pleasing, yeah. Right? I don't know, seeing the graph, to me, that's pretty dramatic to see the graph there. All right, so next issue. Any questions on that? Right? So by the squeeze theorem, we know that has to be removable discontinuity at the point 0, 0. Okay, what about this? Find all vertical asymptotes and evaluate the limits from the right and the left. There's some questions that ask you to do stuff like that. Good questions, that's important stuff to do. So what would we do with this function? We want to find vertical asymptotes and holes. Factor it out. Yeah. Okay, factor it out, top and bottom. So the top's going to factor into what? X minus. And, okay, bottom.
That's what it says. That's what it is.
Oh, okay. I was so confused.
Okay. So what would you expect that to look like?
It's going to have a hole at x equals 3 and a vertical asymptote at x equals 6.
Okay, true.
And there is cross.
And when it would have a horizontal asymptote where?
1.
At 1. Okay, good, good. So,
And there is a 0.
nice touch. We didn't talk about that, but that's good. Okay, so let's go to this one. And there it is, right? Let me turn that one off, okay? As we said, vertical asymptote at 6, horizontal asymptote at 1. And if I try to evaluate this thing at, where's the hole going to be again, you said?
3.
3. So if I let a equal 3, f of a is undefined. So it doesn't show up there, but there's a hole at 3, right? Okay, good. Just as expected. Okay, what about How about this one? Same thing, right? Factor top and bottom. What's it factor into?
X minus 3, x minus 5, all over x minus 3 squared.
Okay. Okay. What do we get?
A whole
X
x
minus
plus 1. And the vertical asymptote is basically half of
Okay.
Okay,
So there's a little bit of a dilemma, isn't there? Right? Because if we write this as x minus 3 times x minus 5 over x minus 3 times x minus 3, yeah, a little uncertainty there, isn't there? Okay, the answer is there is no hole there. It's a vertical asymptote. Okay, but why? I'll prove it to you.
If you got rid of the hole, it'd still be an asymptote. Also, the asymptote would go infinite amount.
So if we grab, that's just this one right here, right? I don't know why it does that. Well,
It's so undefined, it's undefined in two different ways.
yeah. So there's the function, vertical asymptote at 3 and no holes. Okay? Why? Can anybody justify that? That's a pretty sophisticated question, really. It doesn't show up a lot in stuff like this, but what's going on? If I were to take a limit here, the limit of, if there's a hole, I should get a finite limit, shouldn't I? Right? So the limit of g of x as x approaches 3, if I try to evaluate directly, what am I going to get? 0 over 0, right? What's 0 over 0 mean in terms of a limit? More work, right? It's indeterminate. Well, what could I do to resolve the indeterminacy?
Get rid of top and bottom factors.
So I could cancel that one with one of those, right? And now if I take my limit,
And you get -2 over 0.
I get -2 over 0. That is not indeterminate. What's that? Infinity. That means vertical asymptote, right? So there's a really important moral to the story here, and something that I think, I don't know, I think I probably kind of misled you on this, 'cause I'm sure at one point I made the statement, if you get 0 over 0, it's a hole, right? Well, in most cases it is, but it's not in this case. So what's the difference? How can we figure out? How can we undo? I wish I could unsay that statement, because I know I probably said that at some point. So how can we see there's a difference here? Well, there's a couple ways you can think about this. If you have an indeterminate result like that, when you try to evaluate a limit at 3 in this case, and you get 0 over 0, it really is indeterminate. It might end up being that you're going to get a finite result, which is going to be like up here in this previous example. If we had taken this limit as x approached 3, what would we have gotten? -2 over -3? We would have gotten 2/3. If the limit is finite, then that means a hole, doesn't it? Right? So that, it really was a hole. But if when we resolve the indeterminacy, we end up getting a number divided by 0 when it's infinite, it means it really wasn't a hole. It was indeterminate, but it didn't work out to be a hole, right? We could see that in the fact that this factor was squared on the bottom, right? So if you have a multiplicity of a factor that's greater than 1, that's when this kind of thing is going to happen. Here's another way to think about this. Think about power functions of x. Okay? So what if we take the function h of x equals x to the b over x to the c? Well, if b is 1 and c is 1, that's just x over x, and we get 1, right? So if we took that limit, we would get 1 for an answer, and that would just be a hole, right? What if the top gets bigger? What if the top is 2? Okay, well, x squared over x to the 1 is just works out to be x, and so once again, we're going to get a hole on this function, but it's going to look like x, which is a line. What if we take x cubed over x? X cubed over x works out to be x squared, so it looks parabolic. And there still would be a hole at 0, right? And You see the pattern. If I did x to the 4th over x, I'm going to get x cubed. It looks cubic, and I get a hole at 0, right? What happens, though, if the bottom becomes a bigger power than the top? Then you get an inverse function, right? Or reciprocal function. Well, what do you notice about that? If c is 2 and b is 1, that looks like 1 over x, and this is what 1 over x looks like. It has a built-in asymptote, right? What if we do x to the 1 over x cubed? Well, I get, once I get a asymptote built in again, don't I? Right? And if, the pattern's just going to keep on flipping back and forth between an odd and an even asymptote function, right? But do you see that in our previous example, it's just exactly like that? If I've got an x cubed, or an x minus 3 squared on the bottom and an x minus 3 to the 1 on the top, if I take the ratio of those, that behaves like a 1 over x minus 3 to the 1, right? Everybody see that? So you really don't get a hole there. Even though it's 0 over 0, this behaves like x minus 5 over x minus 3, right? Which is not a hole. Okay. Make sense? Questions on that? Okay. All right. That's pretty sophisticated, but it came up. It's unlikely you're going to see a lot of that throughout the year, but I wanted you to be aware. Okay, I'm going to shut up. You guys can work and get questions answered. Tomorrow you get a full work day. How's that sound?